Hi there. My name is Professor Michael Miljanovic, and this is the first video in my series for CSC236, Introduction to the Theory of Computation. This video and those that follow it are intended for you, the class, to watch before you come to lecture. In these videos, I'm going to cover the theory behind what we're going to talk about in this course, and when we actually come into class to work together, we're actually going to be applying this theory and using it in the context of different problems and discussing about it, so on and so forth. Now, that being said, if you're watching this before the class has started, good on you. You found this already, and you'll be very prepared for our first lecture. If the first lecture's already gone by and you're watching this after, don't panic. Everything I'm going to cover in this very first video and its sequel are things that should be review for you. Hopefully they're things that were covered in Math 102 or maybe another math course that you've taken, and they're really just the prerequisites of what you need in order for you to understand this course. So, without further ado, welcome to the class. Most likely this is your first CS theory course. And this is much more computer science than something like CSC 108 or maybe even CSC 148. Some of the things that we'll talk about in this course are definitely going to be related to those, and you absolutely need to be very comfortable with the topics that were covered in those two courses if you want to do very well in this class as well. So we're going to start by diving right into all of the notation and basic logic that you really need in order to be able to move forward in this course. We're going to start off with some topics that are a little bit of review. Hopefully you should be familiar with everything that I talk about in this video. If not, you'll want to brush up a little bit, and maybe everything that I'm going to be telling you will help you to remember some of the things that you may have forgotten since your last theory course. So let's start with sets. What is a set? A set is a collection of any distinct objects, which can be literally anything. Most of the time, at least in this course, we're going to be talking about sets in terms of numbers, values. So the most obvious that you can think of is probably the set of natural numbers. What are they? 0, 1, 2, 3, and so on, all going up through positive integers, plus 0. For this entire course, 0 will be defined as a natural number, no exceptions. Integers, which are denoted by this special looking Z, is all of the positive and negative integers and 0. So negative a billion, negative 900 million, negative 2, negative 1, 0, 1, 2, and so on going up the other way. Q, the rationals, are any, so here we'll want to be a little mindful of how we format what a set looks like. So you'll see here all of our sets have been defined using the braces, right? So inside the braces, each element is separated by commas. And in here we have a little bit of a different format, but this is still something that you'll probably see quite a bit in this course, which is before the first colon is the term, the different terms that belong to this set. And all of the elements of this set are P over Q. Now, what are P over Q? Everything after the colon tells you what that is. So P and Q are integers, positive, negative, or 0. Q cannot be 0 for any element of the rationals, which makes sense. You can't divide by 0. And also, for whatever P, Q we have in this, the greatest common denominator of P and Q is 1. So what I'm saying here effectively is that in the set of rationals, we would not say something like 4 over 6 is one of them, because there's no point in saying that. You could just say 2 over 3. Right? It's simplified. The greatest common denominator is 1. You wouldn't say that 4 over 6 is in the rationals, because you could just say, well, 2 over 3 is, and they are equal. This is important because otherwise this set would have a bunch of duplicates, and something that we generally try to avoid in most sets is the idea of having duplicates. Typically in sets, each element is unique. There may obviously be cases where that's not true, but most of the time that is. Now, these sets all have lots of different values. Sometimes your set only has one value. For instance, who are the coordinators of CSC236? It's me. It's just me. There aren't any other professors who are coordinating the course specifically. Now, you see this symbol here. You probably should recognize. If not, this is a symbol that shows that an element is in a set. So P and Q are in the set of Z, which means that these values, P and Q, are negative 1 or negative 2 or 1 or 2 or 3 or so on. So 5 is in the set of natural numbers, for example. So what sorts of operations can we do with our sets? Well, the first is union. You can take two sets, and the union of them is the elements that are in either set. So if you want to say this formally, the union of sets A and B is the set of elements X that are in S, S being the set that we create from the union of these, where X is either in A or X is in B, or it could be in both potentially. The intersection is any elements that are in A and B. So you use this little loop to say that it's in this one and this one. It's the elements X that are in the set where X is in A and X is in B. So the easiest way to think about this is using Venn diagrams. So if you want union, any elements that are in either of these, including the elements that are in both. Whereas the intersection is only the elements that appear in both sets. They can't just appear in one set, they have to appear in both of them. So, one question you might ask is, how do you know when two sets are equal to each other, right? So this little symbol here, the C with the underline under it, when you see that A, that symbol B, means that A is a subset of B. In other words, all the elements that are in A are also in B, although B may have more elements potentially. So, how do you show two sets are equal? Well, if all the elements in one set are in the other, and also vice versa, if all the elements in B are also in A, that means that all the elements in one set are exactly equal to the elements in the other set. So if you can show that this is the case, then clearly these two sets are equal. So let's go through a really simple example of this. Suppose we have two sets. A is the set of all integers where x squared is 16. And B is a set of just two elements. It's -4 and 4. Well, how can we show these two are equal? So we're going to do it two ways. First, we're going to take an arbitrary element from A and show that it must be in B. And then we'll do the reverse. Take an arbitrary element in B and show that it must be in A. So if we have an element in X, element X that's in A, X squared must be 16, right? Well, that means that X is the root of 16, positive or negative. If it's the positive root of 16, then it's 4, and that's in B, because we can see that it is. If X is the negative root of 16, that means that it's -4. Oh, that's also in B. So we've shown that any arbitrary element in A must be in B. How about the other way around? All right, well, take an element that's in B. That means that X, our element, is either -4 or 4. All right, well, what's 4 squared? It's 16, so that means that it's in A. And what if it's -4? Well, that squared is also 16, so that means that X is in A. And since we've shown both of these, that means the two sets are equivalent. Now, so far everything that I've been talking about is sort of generic math stuff, right? You can probably find in most math courses. We're going to start delving a little bit more into the logic side of things by looking at predicates. So a predicate, P of some input X, is a function on an input X that always returns a Boolean value, so it can only be true or false. Here's some examples. P of X, where X is a professor at UTM. So it means if X is an apple, this would be false. An apple is not a professor at UTM. If X is me, then this would be true. So it can only be one or the other. Q of X is less than 5. Generally, if there isn't a specific denotation of what the domain is for X, and it seems like it's going to be some kind of numeric value, you should assume that that means natural. However, it's not always the case that we're talking about natural numbers. You know, for instance, X is a professor at UTM doesn't really make a lot of sense for natural numbers. But anytime you start seeing numbers in there, if it hasn't been stated otherwise, you can usually assume we're talking about natural numbers, especially in the context of computer science, which is where most of this is going to be applied. R of X, X is false. Kind of a weird and confusing predicate, but you know, this means that if X happens to be true, then R of X is false. And if X happens to be false, R of X is true. Sort of strange. T of X, Prof. Michael is the cool guy. It turns out this has nothing to do with X, but it's still a predicate because it's a function that, sure, it has an input, it returns a Boolean value. So this is either true or false. I'll leave it up to you to figure out which it is. That's your decision. All right, if then, this is pretty important for logic. We want to be able to take a claim and use it to show that something else is also true. So generally when we're using the words if and then in English, this means implies with the arrow that has the two lines and the point at the end. So you would say something like this. If you have p of x implies q of x, in English says, if p of x is true, then q of x is also true. So a simple example of this would be, if it's hot outside, then I will sweat. The predicates here being p of x, it is hot outside, q of x, I will sweat. Now, this doesn't go both ways, right? Just because I'm sweating doesn't necessarily mean that it's hot outside. So there's different layers to this, right? The reason I could be sweating is maybe I'm exercising or something. It's actually quite cold out, but because I'm exercising, I'm sweating, for instance. So it's not always the case that if you have this sort of implication that it goes both ways. Now, this leads us to the idea of vacuous truth. If p of x, the thing that we're saying, if this, then this, is impossible, then the implication actually is always true. And there's a really handy rhyme that I usually use to remind myself of this, which is, if pigs can fly, then so can I. Now, the reason that this is true is because since pigs can't fly, at least in the world that we live in, then I can make any claim based off of that, right? You could say, if pigs can fly, then I clearly have $1 billion. And you can't say that I'm wrong, because in order for me to be wrong, you would have to show that pigs are flying. And since they're not, the rest of the statement is basically meaningless. And we call this vacuous truth, because the first part of this implication is just never true. Now, the converse. Consider p of x being I have an apple, and q of x being I will eat, presumably eating the apple. Now, p of x implies q of x means if I have an apple, then I will eat. The converse of this implication, p of x implies q of x, is q of x implies p of x. So if we break this down, what does that mean? Well, it means if I will eat, then I must have an apple. And the reason that the converse is useful is because of what's called if, and this is not a typo, IFF, if and only if. And the way that you denote this is with the arrow pointing both ways, 2 lines and then 2 points. And this means that both of these are either true or both of these are false, and there's no other possibilities. You can't have one of them be true and the other one be false. They have to both be the same. So you would say that Michael will eat if and only if he has an apple. If I'm not eating, I must not have an apple. If I do have an apple, then I must be eating. If I have an apple, then I will eat. If I will eat, I must have an apple. And this is if and only if. You will see this a fair bit in this course because it usually means that we have 2 predicates that are really strongly related to each other, and sometimes you need to be able to show this by showing that the implication works both ways. Qualifiers are something that we'll also need to tie into our predicates, because so far we've been kind of loose about what happens with the input to these predicates, but it really does matter where our predicate is defined, and that's where qualifiers come into play. So the first of these is for all, so the little V, upside down A, I guess. And so you might see something like this: for all n in some set S, P of n, meaning P of n is true. And what this means is that for every element n in our set S, our predicate P of n holds true. It is correct. The other qualifier that we'll see is there exists, and it's the capital E backwards. And so you show something like this: there exists an element n in our set S where P of n happens to be true. So P of n holds for some n in the set S. It doesn't have to for all of them, but there is some example somewhere where our predicate holds true for an element in this set. Now, negation. Not will use this little kind of like rotated L, and this means the predicate is false. In other words, if I have not P of x, that means I do not have an apple, going back to our original P of x being I do have an apple. If you negate a qualifier, this means that you switch the qualifier to the other one. So here's an example of that. Suppose you have our predicate E of x, which is x is even, and suppose we have some statement, there exists some n in the naturals where E of n is true. this kind of makes sense, right? There is an even number. I'll go with 2. 2 is even. So there is at least one even number, which is, we would say, is correct, right? If you want to negate this, you go through here and you pretty much apply negation to every part of it, meaning that there exists becomes for all becomes there exists, and if there are predicates, they become not that. So the negation of there is at least one even number becomes for all natural numbers, they are not even. And we know, of course, this is false because, well, there is a natural number that is even. It's 2, the one I said. So the reason that negation is helpful is because of something that's called proof by contradiction. Sometimes it's easier to show that a statement is true by looking at the negation and showing the negation is false. Because if the negation is false, then the original thing must be true, just by logic. So let's take an example for this. Suppose we have a predicate, s of n, which is there exists a rational positive number smaller than n. And suppose we want to show that for all rational numbers, s of n holds true. When you think about this kind of makes sense, right? If you grab any rational number you can think of out there, there's a smaller one, right? Whatever really tiny number you can think of, you can probably do some operation on it to get a smaller number. Now that being said, if our goal was to grab every single number out there and prove that for all of them there's a smaller one, that could be annoying. So it might be easier to instead look at the negation. The negation is, we flip the signs, we make the predicates false. There exists a rational number where s of n is false. In other words, suppose there is some rational, and we'll call it q, where nothing is smaller than that. Now, well, what happens if we just took q over 2, right? Q over 2 would also be a rational positive number. It's smaller than q, but we said that q is going to be something where nothing is smaller, so how could we possibly have come up with something smaller? Clearly, this negation must be false. So if our supposition, the negation, is false, then our original statement must be true. And so by proof of contradiction, we've shown that for all numbers in the rationals, s of n holds true. I should say positive rationals. I should probably have a little plus there, but I think hopefully you get the idea.